A university, 70% of students are undergraduates and 30% are postgraduates. Amy and Rob want to do a survey. Amy decides to do a random sampling to collect a sample of 100 students. She uses a university database to sample frame. She numbers each student on a database. She then generates exactly 100 numbers and then uses random numbers to select a sample. Give 2 reasons why Amy methods might not produce a sample of 100 students. Right, first of all, if she's using a random sample, there is a chance the same number might come up twice. Because that's how random sampling works. Then obviously you wouldn't get 100 students, you get 99. Some of the students, when they get selected, they might not want to take place or take part in it. So that means that they also won't be selected. You could also say that maybe that there isn't enough numbers to be linked up to the pupils. Right, next one. Robert decides to use quota sampling to get a sample of 100 students. He plans outside the main building and has interviewed 70 undergraduates and 30 postgraduates. Give 2 advantages of using quota sampling. So just to remind you, quota sampling is you keep interviewing until you get the 70 undergraduates or the 30 postgraduates. So one of the main advantages are that you can compare the 2 groups. Okay, it's quite easy, because he stands outside and he can do it as they arrive. Okay, explain why quota sampling is not random sampling. Well, because by its nature, not everyone's got an equal chance of being chosen. If you think in his university you've got the same number of undergraduates as you do postgraduates, your undergraduates are more likely to be chosen than your postgraduates. Okay, the population pyramid shows information about the numbers in thousands of drivers of each gender who made car insurance claims in the UK in 2015. Males on the left, females on the right. How many female drivers aged 50 to 59 in the UK in 2015 made car insurance claims? So 50 to 59. So that one there, we just read it down to here. Okay, 5, 6, 7, 8, 9. So it's going to be 9,000. 1, 2, 3. Don't put 9. Clearly that don't make sense. Right, the population pyramid shows that the age group which has the fewest number of drivers who made car insurance claims is the 17 to 19 group. I know it does. Yep, good. State a reason for this. Now, there could be a few reasons. You could say that they're young drivers, so there's not a lot of those people out there on the roads because they haven't passed their test yet. You could also say that a lot of people, they tend to be put on their parents' insurance, so if they crash, wouldn't be showing up on there. You could say that maybe because they're new drivers, they're very cautious. They don't like to drive on motorways or anything like that. Try and use your knowledge of people for that one there. Okay. Right. Okay. In 2014, the number of male drivers aged 20 to 49 in the UK made car insurance claims was 66,700. Compare the number of male drivers aged 20 to 49, which I marked there, in the UK made car insurance claims in 2014 with the number of male drivers aged 20 to 49 in the UK made car insurance claims in 2015. You must show you're working. So let's work out how many it is. Okay, so it's going to be 25, which is the first one. That one there is going to be 21. This one here is going to be 15, 16, 17, 18, 19. Let's add them up. And just remember, these are all in thousands. It's 25 plus 21 plus 19, which is 65,000. Sorry, no, the other one is 66,700. So you'd have to say a sentence along the lines of, in 2014, the number of male drivers aged 20 to 49 in the UK made 1,700 more claims than the number of male drivers in 20 to 49 in the UK in 2015. Okay, make sure you're specific about what you're saying, otherwise you won't get any marks for it. Okay. A safe drive insurance company charges young male drivers more for car insurance than it charges other drivers. You can explain 2 features, it's important, of the population pyramid which Safe Drive might use as a justification for doing it. So actually look at the question, because what some people tend to do is that they do male young drivers as one sentence. It's really male drivers, and then it's young. That's where you're getting your 2 points from. So first of all, you'd say that there are more claims by male drivers than there are female drivers. And your second one is that apart from 17 to 19, there is more claims by young drivers than there are by older drivers. So just make sure you've got 2 separate points to get your 2 marks. Jeremy says, the population pyramid shows that the total number of male drivers in the UK in 2015 is greater than the total number of female drivers in the UK in 2015. Explain whether or not Jeremy's conclusion is appropriate. Now, from the population pyramid, that only shows the amount of claims. It doesn't show the amount of drivers. So you can't make that assumption. Okay, so no is not correct for that reason. Okay. Vicky says in the UK 2019, there'll be more male drivers who make car insurance claims than female drivers who make car insurance claims. Explain whether or not the information in the population pyramid can be used to support Vicky's statement. No, you can't be, because it's for 2015 and 2019 is totally different year. And the easier way to explain it, imagine that actually is for 2020. Yeah, it'll be totally different because obviously due to the pandemic, there's a totally different number of drivers on the road. The frequency polygon shows information about the world times taken by 49 athletes to run 400 meters in the 2017 World Championship. Now use this information, the frequency polygon, to complete the table. Okay, now if you actually look at part C, we're going to have to estimate the mean, and the mean's always easier from a frequency table. So I'm actually just going to draw a frequency table now. Okay? And it's going to be 50 to 51, 51 to 52, 52 to 53, 53 to 54, and 54 to 55. Because if you was plotting a frequency polygon, you'd always do it from your midpoints. Now I'm going to write the midpoints here because it's going to come in handy later when I do my mean. Okay, this is 50.5, 51.5, 52.5, 53.5, and 54.5. These are the midpoints. Now let's read them off. Each square is 1. So the first one is 4. And my second one is going to be 16. And my next one is going to be 20. This one here is 6. And that one there is 3. Now, using the information in the frequency polygon to complete the table I'll write in, which one's 6, it's going to be 53 to 54. None of the athletes run 400 meters in exactly 53 seconds. Find the number of athletes who run 400 meters in less than 53 seconds, okay, which is going to be my top 3. Okay, so 20 plus 16 plus 4, which gives me 14. Okay, calculate the estimated mean. So for the mean, first thing we've got to do is we actually multiply your midpoint and your numbers. Okay, so I've got to do 50.5 times 4, okay, which is 202. 51.5 times 16, which is 824. 52.5 times 20, which is 1050. 53.5 and 6, which is 321. And 54.5 times 3, which is 163.5. I'm just going to add them up. Which would equal 2,560.5. I need to divide them by the amount of people there are. And people tend to go 1, 2, 3, 4, 5. That's not right. The amount of people would be the total of this column. Now you can add them up. It'll be 49, but you can just read the question because 49 is here, 49 athletes. So I need to divide it by 49. And I get the answer 52.255. Now, check them to see if it makes sense. 52 is about there. That's about right, and I think that's fine. Randall used the internet to find a number of points scored by each of the winning teams in the last 30 years of Super Bowl. He drew a stem and leaf diagram. Write down 2 improvements Randall should make. Stem and leaf, I'll be honest, you don't even have to look at these to know it's always going to be that there is no key, and it's probably always going to be that they're not in order. Tulsa Breeze they are. Yeah, not in order. Okay. Part B, assess the reliability of using the internet as sources of Randall's data. Now, there's 2 ways you can go. Right, you can say the internet is a secondary source, so the reliability can be questioned. Yeah. You could comment on it depends if the website is official or not. Now, this one here is NFL.com. If you know football, NFL.com might be the official one. So if NFL.com is the official website, then this is obviously reliable. However, it could be one trying to be the official website, so then it's not reliable. Okay. Now you've got to think again because it is secondary data. If it's not reliable, it could just be somebody just making up the scores, and sometimes they could be leaving out certain data. So try and always think where it comes from. Randall believes the number of points scored by the winning team is increasing over time. Comment whether or not Randall represents the data in an appropriate diagram. I'll say no, that's not suitable. A semi-leaf does not show changes over time. You'd need something like a time series graph. That'd be perfect for this. Figures below show the amount in millions of UK given to Ethiopia for the years 2009 to 2015. The table gives a summary in millions of UK of aid given to Pakistan for 3 years 2009 to 2015. Compare the amount of UK and Ethiopia to the amount of UK given to Pakistan from the years 2009 to 2015. You may use blah blah blah. All of it squared equals 631,217. Okay, so what I'm going to do is I know this is for Pakistan, and I actually wanted to do the same numbers for Ethiopia, because then I might have got data that's scored, and let's be honest, I'm giving you this data not to compare it. Okay, so the greatest number here is 344. Okay, the mean, so let's add them all up and then divide them by the amount of scores. So 219 plus 263 plus 344 plus 265 plus 329 plus 321 plus 338, which is 2079. I've got to divide them by 1, 2, 3, 4, 5, 6, 7. So my mean is going to be 297. Okay, now you are given two formulas. Doesn't matter which one you use, but here I've got the sum of all the scores squared. So that tells me it's going to be doing the second one. Now, a common mistake people do is that when they do the mean squared, and then when they do the average of the scores squared, they tend to do it the wrong way around when they subtract. Now, obviously, one way you should get a positive answer, because with square root you can't do the negative. So if you do it the wrong way around, just ignore the negative. So I'm going to do 631,217. Now I know there's 7 scores, so I'm going to divide it by 7. I'm going to take away to my mean, which is 297 squared. All of this is square rooted. I'm going to type in exactly how it says in my calculator. 1217. All of that over 7. Minus 297 squared. Which gives me 44.32. This is 44.32. And I need to do a statement. One statement comparing my means. So I have to say that Ethiopia, on average, has got a higher aid than Pakistan. And I have to say, but however, the standard deviation is 44.32. Telling me the scores are closer together for Ethiopia than they are for Pakistan. On July 2015 is the base month. The table shows index numbers for the Consumer Price Index in 2015 to 2017. Given an interpretation of 103.2 in the table. Okay. So don't do anything flash. 103.2 just means 3.2% increase from 2015. Okay. CPI is a weighted index. It measures the changes in the prices of consumer goods and services only when the weightings are shown on the table below. Using July 15 as a base month, the index number for the goods is 2017 was 100.7. Calculate the index number for services in July 2017. Now, what you've got to understand really is that this one at the top, this original index number, that's an average of your goods and your services. So you need to try and remember how to do your weighted average. Yeah. Now, your weighted average would be get your weight, which is 525. Yeah. Times the actual number, and for goods we got 107, so 100.7. Yeah, and then we're going to do the other weighted, which is 475 times, and that's what it's asking for. So I'm going to call this X. Okay, let's put some brackets in. Not that you need it, but it just makes you understand what's going on. And that's got to be over the total weighting, which is 525 plus 475. Okay, and all of this is going to equal 103.2. Because that's my actual weighted average at the top there. And all we have to do now is solve it. So I'm going to times both sides by 525 plus 475. So times them both by 1,000. Okay. Or 103.2. Okay, which gives me 103,200. And then I've got 525 times 100.7. So I'm going to change that to 5286.7.5 plus 475x. So I'm going to minus both sides by 52,876. 103,200, which gives me 50,332.5 equals 475x. I'm going to divide both sides by 475, which gives me the answer of 105.96. Okay, right. Let's see. One of the items included in the goods index is food. Assess whether or not it's appropriate to use 100.7 in order to find the estimate of the change in price from food from 2015 to 2017. And this is not appropriate really because we don't have enough data, and we know that because it's a combination of those two, those weightings might change. So we can't make any assumptions. Susie is investigating the amount of time students is spending watching TV. She randomly selects a sample of 50 students from the school and asks them the following question. Right, so there's questions here. I'll do it one by one. Pause the video if you want to have a try for yourself. Right, so first one in red. Give a reason to support using a histogram to represent the amount of time students at her school spend watching TV. Now I say time is a continuous variable and histograms are good for continuous variables. And that's it. Okay. Right, for B, complete the histogram. Now this says frequency. This says frequency density. They are not the same. Please do not think they are the same. Now, because this is not really in the normal form, I like to put down the boundaries of these class. So the lowest one there is 1.5 and the highest one is 2.5, 2.5 to 3.5, 3.5 to 5.5, 5.5 to 7.5, 7.5 to 11.5. Okay. Now we could do class width and we need the frequency density. Okay. So my class width here is 1, that's 1. 3, 4, 5 is 2, 5, 6, 7, which is 2, 7, 8, 9, 10, 11, which is 4. Frequency density is your frequency divided by your class width, which is 14. Good, that matches up to this. 11, 4.5. This one here is 2.5, and that's 1. Okay, now we need to plot these. So here is 2.5, which is there, and it goes all the way up to 7.5, so that's 7, 7.5 is there. And it looks a bit weird because it's not strictly where we'd normally be drawing them if we drew it ourselves. And the other one is going to be the height of 1. That's 2.51 is going to be there. And it's going to go all the way up to 11.5, which is there. Okay. Okay. Now, a student is selected at random from those in this sample who's watching less than 5.5 hours of TV. Estimated probability the student would watch less than 2 hours of TV last Saturday. So less than 5.5. And so you just think, that's actually, I can just read that off my thing because 5.5 is going to be these three people here. Yeah, so 14, 11, and 9. Okay, so that's my entire range. Like people above 5.5, they are not included. Now we want the probability that is less than 2 hours. So less than 2 hours is actually exactly halfway between that on there. Okay, so essentially this has got a height of 14, yeah, which is there, and I think that length there is estimated to be 0.5. So there's only 7 people who are less than 2 hours. So 14 plus 11 plus 9 is 34. So it's going to be 7 over 34. Type into my calculator, and that stays as it is. Okay. Right, so using the midpoint, Susie calculated the mean time spent watching television to be 4 hours. She concluded that the mean time spent watching TV in full days must be 7 hours for all students. Assess how Susie's question might affect the accuracy of the mean time. I'd say because she used midpoints, that's not accurate, that's an estimate. So for example, the group 4 to 5, everyone could actually be 4 hours of TV. And then you've actually put the midpoint of 4.5. Okay, and I'd also look at the questions. I'd say there's no options to do like 1 box 0, so 1 hour, 0 hours, above 12. Okay, all students, you got to focus on that one there because she's looking at students in a school, so it's just students that she spoke to. Okay. And she also says each day, yeah, which really the question is really just for Saturday. Yeah, so there's quite a lot of things wrong with that one there. Assess how Judy's method for collecting data affects the validity of her conclusions. Okay. Well, first of all, I'd say that it's a random sample, yeah, which is good, which means everybody's got a good equal chance of being selected. I'd say, however, it is from her school, so that means you can't really apply those findings to the wider context. You can only really do it to her school. I'd say last Saturday as well means that you can't be applied to other days in a week. And that's about it. The table of the time series graph gives the information about the number in thousands of visitors to the British Museum each quarter. From 2015 to 2017. Right, explain why it's appropriate to calculate a 4-point moving average for this set of data. So I'd say the year is split up into quarters and the pattern repeats. Or you can say that every 4 data points, that's when the pattern repeats. The 84-point moving average is 1,525. That's a bit of a clue here because you can see all the other pods are 2 apart. So you know it's 2 apart, which means it's going to be up here. Okay, and it's not. Don't look at things between 1 and 2. It's not. It's essentially between 4 and 3 because that's the middle point of all your averages, and it's moved up to 1,525, 1,500. So it's going to be halfway between there and there. Okay, draw a trend line for the graph. Essentially, it's just the same trend line of best fit, but I can't do it with a pen. So I'm doing that. Okay. The average seasonal effect of quarter 4 is down to be minus 144,000, given interpretation of this value. Well, I'd say that this means that the actual value for quarter 4 is expected to be below the trend line by 140,000. Calculate an estimate for the number of visitors to the British Museum in quarter 4. So we read quarter 4, I'm here, yeah, by going up. So I'm just going to go across that line. It's quite hard to do. Which is there, so I'll have to put 1,450. Now I think it's going to be below minus 140. So I've essentially got to do that sum. So 1450 minus 140. So I've got my answer of 1,310. Okay, write down 2 assumptions that have to be made in your estimate part D. Make sure if there's 2 assumptions, make sure they're 2 clear different assumptions. So my first one is that I assume that the seasonal trend effect is going to be the same. And I'm going to assume that the actual yearly trend or the line of the trend will actually be the same as well for next year. To apply for a job, an applicant must take a numeracy test. Tables give information about the test taken by all applicants. To get an interview, an applicant must score a standardised score at least 1.5 for the test. Martha scored 68 in the test. Decide whether or not she gets an interview. Well, if standard deviation is 8, then we can think that as a 1 standard deviation. 1.5 means that 8 times 1.5 is 12. So I need to make sure that it's either 12 above or 12 below the mean. Because it's clearly above the mean, I'm going to do 12 plus 55, which is 67. Yeah, she gets an interview by 1 mark. Alex's standardised scores for the test is minus 1.25. Fiona's score for the test is minus 1. Compare their performance with each other and give reasons for the answer. Now I'd say that Alex did 1 1/4 standard deviations below, where Fiona did 1 standard deviation below. So Fiona did better because hers is closer to the mean than Alex's. Right guys, let's go through this then. So Noah starts investigating reaction times of athletes. He collects 50 data. Yeah, here's the reaction times, the lowest and the highest. Here are sums. So we've got the sum of all of them, the sum of everything squared. The number of people, yeah, the standard deviation and the range. He decides to clean the data. He models reaction time using the distribution. Yeah. Right. So we actually will need to work out what the mean is. Yeah, and then we're going to have to work out what's 3 standard deviations above and 3 standard deviations below. Now there's obviously a lot of information here and you need to ignore some of it. So mean, normally you'd add up all the scores, which is actually that one there, the sum of the scores. So it's going to be 88. I'm going to divide it by the amount of scores, which is 50, okay, which gives you 1.76. I've got my standard deviation as 1.05. So I want 3 of these. So I sort of like need to do plus or minus 3.15 to get my lower and my upper bound. Let's do the upper bound. So 1.76 plus 3.15 is 4.91. And my lower bound is going to be 1.76 minus 3.15, which is minus 1.39. Obviously, this is like hypothetical because you're going into minus numbers and we're talking about reaction time, so it makes no sense. So which scores are above 4.91, which is these two, yeah. But so you'd have to say 5.3 and 5.7 are outliers, as they're 3 standard deviations above the mean. I've got to say, guys, it's important to have both of these numbers, or 4.91 and 0 as your lower bound. Yeah, you do get marks for that. Okay. Have we got right, Gazzelli collected data about the age and range of a small company. She used statistical software to draw a scatter graph. Okay, give one advantage. You can say reduces human error. It's quicker, it's easier, something like that. Right. So she's got 2 correlations. Spearman says 0.95 and Pearson says 0.77. Describe and interpret the type of correlation. Right. Describe, I'd say it is a strong positive correlation. Interpret, I will say that as the salaries increase, the age also increases. Okay. It's important to do both. Yeah. Which of the 2 correlation coefficients in the table best represents a stronger correlation? I'd say Spearman's represents stronger correlation because it's closest to 1. I'd use those exact words. For C, which one of these 2 diagrams most likely represents the data? Now, if you look at one, one's very linear and one's a lot less linear. Now, because Spearman's is higher, yeah, Pearson's you can only use for linear data, so this actually looks like it's Spearman's because it's higher and so less linear. Okay, Brett wants to use the Pearson's product moment correlation coefficient to compare the salaries of male employees and female employees. Explain why it's not appropriate. Well, essentially because you need bivariate data for Pearson's moment correlation coefficient. Okay, if you don't know what that means, essentially think about it, you need a data point to connect to like scores. So you could say that what is a pupil, we compare a stats scores and the maths scores of a school because those pupils will do maths and stats. Yeah, but there isn't somebody in that employee who earns a male wage and earns a female wage. So I say those 2 scores are not related enough. Okay, Jasper has 3 coins. In an experiment, he flips 3 of the coins and records the total number of heads he gets. Jasper believes that the coin is biased. That the number of heads he gets can be modeled by the distribution B brackets 3, 0.4. So that the probability of 0 heads is 0.625. Now, what we need to do is think about how does a binomial distribution work. And I always like drawing Pascal's triangle. Yeah, and this is fairly easy to work out because all you're doing is adding the ones above it. Now, most of the time you are given this, so I'm surprised this one you're not. Again, now because we've got 3 coins, you've got to think you've got 4 outcomes. And if you look a little bit further down onto part C, you can see the 4 outcomes. So we're going to be doing this one here. And I actually like just listing out all the outcomes too. So I know that P, if I think P's probability the event is happening, which is 0.4, yeah, which is there. I know that Q is going to be 0.6. And then we just got to remember the distribution. So I know that P to the power 0, yeah, and it's going to be P to the power 1, P to the power 2, P to the power 3. Right, Q works the other way around. So 3, 2, 1, 0. And then the reason why I put this box in is because that's going to be your coefficient. So 1, 3, 3, 1. And if you remember this expansion, each one represents an event. And I like to look at the P's because I know that P cubed is going to be that event happening 3 times. This one here is going to be 3 heads. That one there is going to be 2 heads. That one there is going to be 1 head. And that one there is going to be no heads. Okay, now let's actually just focus on the question. So there's a probability of no heads. Okay, so I'm using this one here. So it's going to be 1 times P to the power 4 no times, yeah, times 0 to the power 6 3 times. Okay. Now this does simplify down to 0.6 cubed, if you just did that. Okay, and I've got 0.216. I'm going to write it here just because it'll help me out later. The answer here is 0.216. Okay, so change colours. Work out the probability the experiment has exactly 1 head. Okay, so exactly 1 head is going to be this one here. Okay, which is 3 times 0.4 to the power 1 times 0.6 squared. And you essentially just type that into your calculator. And I've got 0.432. 0.432. I'm going to write this down for one head. Okay. He carries out the experiment 100 times. The table shows information about the number of heads he gets from the experiment. Determine whether or not the model of B3, 0.4 is suitable for Jasper's experiment. Now I've worked out the probability for the next two. Yeah. So whether you need to or not, I'm going to do it anyway. Let's do it for the next one as well. So if I'm doing it for two heads, it's going to be 3 times 0.4 squared times 0.6 to the power of 1. 3 times 0.4 squared times 0.6, which gives me 0.288. And my last one, I'm just going to do p cubed, but I've run out of space, so I'm not really going to do it. So it's 0.4 cubed, which is 0.064. Now that's the probability of each event. If we're doing 100 times, we're just timesing it by 100. So I'd expect my first one it to happen 21 times. My second one I expect to happen 43 times. My next one happens 29 times. My last one I think will happen 6 times. Now if you look at like what we expect to happen and what actually happens, it's not exact, but it's sort of like there. It's roughly about the same. So I'd say, yeah, I'd show my working out, and I'd say that I think this is a good model because our predictions are roughly, yeah, what he actually found in this experiment.